Welcome back to the deep dive. Today we are strapping in for, well, the ultimate shortcut. A really comprehensive deep dive into the cosmos itself.
Yeah.
We're diving into the fundamental science of the universe, using all the rich material you've shared with us.
Our mission really is to get rapidly well-informed on astronomy, cosmology, astrophysics, the whole lot. We're basically synthesizing everything from, those ancient observations of heavenly bodies right up to the modern physics that tries to explain their behavior, their properties, and these incredible motions out in space.
And when we say astronomy, we really mean the full scope, right? Sun, moons, stars, planets, comets, gas, galaxies, dust, cosmology too, and all the phenomena that, well, govern existence.
Exactly.
It's not just spotting objects, is it? It's about getting underneath to the deep physics.
Precisely. And maybe to set the stage for just how immense this topic is, let's think about the breadth of the journey we're taking. We'll start with, the ancient history of stargazing, and we'll travel all the way to the most modern, really profound mysteries like dark matter and dark energy.
Wow.
And it's kind of astonishing when you stop and think. These two components, they make up something like 95% of the entire universe.
95%. So the visible world, the stuff we think we know.
Just a tiny fraction of this story really puts things in perspective.
Okay, let's start with the name itself, astronomy. You mentioned it comes from the Greek astron for star and nomos. What was that? Preparation or rule?
Yeah, preparation or rule. And that kind of hints at this long history of trying to bring some order to, well, the apparent chaos of the night sky.
Makes sense.
And that origin points exactly to the kind of precision the field needs. More accurately, you could say astronomy is the study of the source and the growth of the universe, plus the chemistry and physics of all the cosmic materials, and importantly, estimating their locations and their motions. It's fundamentally about understanding the genesis, the evolution of everything we see, and crucially, what we can't see.
Right. And it's worth remembering, isn't it, that early astronomy was much more, well, practical.
Oh, absolutely. Primitive people, they used the motions in the sky to figure out where they were, both in space and time.
Like finding their way?
Exactly, and planning things. This knowledge helped them plan hunting, gathering, figuring out the seasons. Early farmers knew when to plant and harvest based on the stars.
And sailors navigating the oceans.
Absolutely. They could navigate the open seas just by detecting the locations of the stars. For centuries, actually, astrography, which is just the accurate measurement of star and planet locations, that was the main profession. And this practical use also explains that historical link to astrology. The skill of trying to forecast future events based on where the planets and stars were, that was considered part of astronomy for centuries. It was part of the astronomer's job.
So the court astronomers were also doing horoscopes, sort of?
In a way, yeah, at least partially. That was part of the gig for a long time.
So what was the big split? What changed to really separate astronomy from astrology?
Well, it was really the scientific revolution. Big advances in mathematics, combined with creating new experimental tools that gave rise to modern astronomy.
New tools like telescopes.
Telescopes were huge, yes, but also the math. Specifically, studying gravity led to what we call celestial mechanics, or physical mechanism. This new branch was revolutionary because, for the first time, it allowed the motions of astronomical objects to be predicted mathematically based on universal laws, not just observed patterns, but actual physical laws.
That's the key difference, then. Prediction based on physics versus assumed influence.
It's exactly right. Astrometry and celestial mechanics developed into the two major areas, and astrology got kind of demoted to pseudoscience. Serious scientists didn't pursue it anymore.
And then things really took off in the 19th century.
Yeah, later on, discovering the electromagnetic spectrum and the whole world of particle physics that spurred the growth of astrophysics, which is now, arguably, the most significant discipline within the whole field.
Okay, speaking of disciplines, maybe we should map out the landscape of modern astronomy, because it sounds like it's way more complex than just looking to a telescope.
Oh, it is. Today, it covers several specialized disciplines. You've still got astrometry, focusing on measuring locations accurately, much easier now with computers and CCD cameras, of course.
Right.
Then there's stellar astronomy, studying how stars form and grow. Galactic astronomy looks at the structure and workings of whole galaxies.
And astrophysics is the physics part.
Yep, applying physics to understand the cosmos and its components. And cosmology?
Yeah.
That's the big picture stuff, the source and development of the entire cosmos.
And you mentioned related fields, too, ones that blend in biology or geology.
Right. You've got planetary science, studying planets, obviously, but also astrobiology, comets, asteroids. basically asking about the probability of life elsewhere.
So a modern astronomer needs a strong physics background.
Absolutely. Specialized astronomers today usually have a really sturdy background in astrophysics. Their interpretations are almost always viewed through an astrophysical lens. It's this constant back and forth, a repeated discussion between theory and observation.
It's also worth pointing out, isn't it, that it's not just professionals driving this. Amateurs play a role too.
A vital role. Yes, absolutely. Amateur astronomers make huge contributions. Many serious amateurs actively study variable stars, or they're the first to spot new comets or asteroids. Often, their discoveries trigger the professional follow-up studies,
Yeah.
##shagtag 1.2 chronology of significant astronomical innovations.
Okay, this is where it gets really cool for me connecting these ideas to actual history. People have been tracking things in the sky since, well, forever, basically.
The timeline is immense, yeah.
Yeah.
If we look at the big innovations, way back, like 30,000 BCE, we find these bone carvings that seem to show the phases of the moon. Really early accounts of basic observation. Wow. Then jump forward to 700 BCE, Babylonian astrologers start keeping records, forecasting things like planetary alignments, eclipses,
Getting more systematic.
much more. Then around 280 BCE, you get Aristarchus proposing the first sun-centered heliocentric model. Pretty radical idea for the time.
But that didn't stick, did it? It was the Earth-centered model that lasted.
Right. Around 140 CE, Ptolemy designs his really elaborate Earth-centric system, with planets moving on these complex circles within circles.
Epicycles.
Epicycles, exactly. And the crucial thing is, despite being factually wrong about Earth's position, his model worked pretty well for predicting where the planets would appear in the sky.
Good enough for over 1,000 years.
Good enough for over the 1,000 years, yeah. It
Yeah.
was incredibly successful, even if fundamentally incorrect.
Yeah, and astronomy didn't just stop in Europe during the Middle Ages, right?
No, absolutely not. Arab, Chinese, Persian astronomers made huge contributions, preserving knowledge and making new observations, while things were relatively quiet in Europe. But then, the Renaissance, the scientific revolution, that changed everything.
Okay, picking up the timeline again.
Right, so 1543 CE, Copernicus publishes his big work, bringing back the heliocentric model.
What a huge moment.
Massive. Then 1609 CE, Galileo points a telescope at the sky. That's really the dawn of modern observational astronomy. He saw things that directly supported Copernicus.
Moons around Jupiter, phases of Venus.
Exactly. In 1682 CE, Edmund Halley uses Newton's new physics to predict the return of a comet.
Halley's Comet.
The very one. A huge validation for Newtonian mechanics.
Okay, moving faster now into the 19th and 20th centuries, physics starts playing an even bigger role.
Definitely. 1842 CE, Christian Doppler describes the Doppler effect, how the wavelength of light or sound changes if the source is moving towards or away from you.
Which turns out to be crucial for understanding the universe's expansion.
Absolutely essential. Then 1916 CE, Einstein publishes his theory of general relativity. The math itself pretty much predicted an expanding or contracting universe.
But he didn't like that idea initially.
No, he assumed it must be static, so he added that cosmological constant to hold it still, mathematically speaking.
Until Hubble proved him wrong.
Well, prove the universe wasn't static, yeah. In 1929, Edwin Hubble provides the observational evidence, the redshift of distant galaxies showing they're moving away from us. The universe is expanding.
And skipping ahead a bit, the Kuiper Belt.
Right, 1951, Gerard Kuiper theorizes this belt of icy bodies out beyond Neptune.
Which we now know is full of comets and dwarf planets.
Exactly. And then, of course, the space age, putting telescopes above the atmosphere. Hubble Space Telescope launched in 1990. The images are just iconic. Pillars of creation, deep fields.
Mind-blowing stuff. And the source material mentions the James Webb Space Telescope, planned for launch around 2018 as the next big step.
Yeah, the successor, designed to see even further back, closer to the beginning.
Okay, let's shift gears slightly to cosmology. This is the big one, right? Studying the origin and the ultimate fate of the entire universe.
Yeah, the grand narrative. And what's really fascinating about modern cosmology is how it connects the absolutely enormous with the incredibly tiny.
How so?
Well, our understanding comes from relating the behavior of the biggest things we see, galaxy clusters, galaxies, stars, with the fundamental insights from particle physics, dealing with the smallest constituents of matter and energy. Cosmology really is this marriage of the immense and the infinitesimal.
That intellectual journey, as we mentioned, started way back with the Greeks and their Earth-centered models. But the real earthquake was Copernicus in 1543.
Right. He put forward his sun-centered model driven by what we now call the Copernican principle.
Which is?
Basically, the idea that there's no good reason to assume Earth has some special privileged place in the cosmos. It's likely just another planet.
A revolutionary idea. And then others built on that. Brahe, Kepler, Galileo.
Exactly. Refining the observations, figuring out the elliptical orbits, and then Sir Isaac Newton synthesized it all. He was the one who really applied universal laws to the heavens.
Before Newton, it was just describing motions, but he explained why they moved that way.
Pretty much. He realized the force pulling an apple to the ground was the same force keeping the moon in orbit around the Earth. Gravity.
Universal gravitation.
Universal gravitation. He used his new math calculus and his laws of motion to describe this dynamic across the cosmos.
But even Newton hit a wall, didn't he? He could describe gravity's effects, but not how it actually worked across empty space.
Exactly right. That's the famous gravity problem. His laws were brilliant for predicting celestial motions, but the mechanism, how does gravity reach out and pull things? He couldn't formulate a physical explanation for that action at a distance.
So what did he do?
Well, ultimately, he had to appeal to something beyond physics. He suggested matter behaved this way because of God's omnipresence, essentially holding the universe together. A proper physical explanation had to wait another couple of centuries.
For Einstein.
For Albert Einstein, yeah.
Okay, so fast forward 2 centuries. Einstein tackles gravity.
He does. Early 20th century, he establishes his theory of general relativity. And in this picture, gravity isn't some mysterious force pulling things.
It's about space-time itself.
Exactly. Gravity is the result of mass and energy warping the fabric of four-dimensional space-time. Planets orbit the sun because they're following the curves in space-time created by the sun's mass.
A completely different way of looking at it. But the math had implications he didn't initially expect.
Right. One immediate consequence of his equations was that space-time itself couldn't just sit still. It had to be either expanding or contracting.
Which didn't fit with the accepted view of a static, eternal universe.
No, it didn't. Einstein himself believed the universe was static, so he introduced that cosmological constant into his equations. It was kind of a mathematical fudge factor, a weight to counteract the expansion or contraction the theory predicted, forcing it to stay static.
Which led to what he supposedly called his biggest blunder.
That's the famous story, yeah. Because just over a decade later, Edwin Hubble showed the universe wasn't static, it was expanding. Galaxies were rushing away from each other.
So Einstein took the constant back out.
He realized his initial math was actually pointing the right way, admitted the constant was unnecessary, and removed it. That observational proof of expansion really paved the way for modern cosmology.
And if the universe is expanding now,
Then, if you run the clock backwards.
it must have started smaller, much smaller.
Exactly. It must have originated from an incredibly small, incredibly dense, incredibly hot state, the Big Bang.
That theory wasn't immediately accepted, though, was it? There was competition.
Right. For a while, it competed with Fred Hoyle's steady-state theory, which proposed that matter was continuously being created to keep the universe looking roughly the same as it expanded.
But the Big Bang won out.
Yes. The crucial evidence came in 1965 with the detection of the cosmic microwave background radiation, the CMB.
The afterglow of the Big Bang.
Precisely. This faint radiation permeating all of space was a direct prediction of the Big Bang model, and finding it pretty much sealed the deal. It became the broadly accepted view.
But Fred Hoyle, even though he was wrong about the steady state, he gave us something else incredibly important, didn't he? Something connecting us to the stars.
Oh, absolutely. He's credited with major work on the theory of stellar nucleosynthesis.
Which is?
It's the idea that elements heavier than hydrogen and helium are forged inside stars through nuclear fusion.
So stars are element factories.
Exactly. They fuse lighter elements into heavier ones, carbon, oxygen, iron. And then when massive stars die, often in supernova explosions, they blast these heavier elements out into space.
Where they become part of the next generation of stars and planets.
And potentially life. It leads to that profound statement cosmologists often repeat: we are all made of stardust. The atoms in our bodies were literally created inside stars billions of years ago.
That's just incredible to think about. Okay, so the Big Bang is established, but physicists then found some, well, fine-tuning problems. The early universe seemed almost too uniform.
That's right. Observations, especially of the CMB, showed the early universe was incredibly smooth, almost the same temperature and density everywhere. But not perfectly uniform, there were tiny variations.
And the problem was explaining those variations.
The problem was explaining why the variations were so small. According to standard Big Bang physics, without any extra steps, any tiny initial quantum fluctuations should have been amplified hugely as the universe expanded, leading to much bigger variations than we observe.
So how is this solved?
In 1980, Alan Guth proposed what's called inflation theory.
The idea of a super fast expansion right at the beginning.
Exactly, an incredibly brief period, a tiny fraction of a second after the Big Bang, where the universe underwent an exponential, faster-than-light expansion.
Faster than light? Is that
Yeah.
possible?
Space-time itself can expand faster than light. Objects within space-time are still limited by light speed. This rapid inflation would have stretched those initial quantum fluctuations across vast distances, smoothing out the universe and explaining the large-scale uniformity we see, while also seeding the tiny variations that eventually grew into galaxies.
And does the evidence support inflation?
Yes, astronomical observations since 1980, particularly detailed measurements of the CMB, have strongly supported the predictions of inflation theory. It's now the consensus view among most cosmologists.
Okay, so even with the Big Bang and inflation giving us this incredible framework, there are still these massive mysteries left, aren't there? The stuff that makes up the other 95% of the universe.
Absolutely. The two biggest puzzles in cosmology and astrophysics today concern the stuff we can't see. First up, dark matter.
What's the evidence for that?
It comes primarily from observing galaxies and galaxy clusters. Astronomers notice that stars, especially those in the outer regions of spiral galaxies, are orbiting way too fast.
Too fast for what?
Too fast to be held in orbit just by the gravity of the visible matter. The stars, gas, and dust we can see. The galaxies should be flying apart, but they're not.
So there must be extra gravity from something invisible.
Exactly. There has to be additional, unseen mass providing the extra gravitational pull needed to hold these galaxies together. That unseen stuff is what we call dark matter.
And how much of the universe is it supposed to be?
Current estimates suggest it makes up around 25% of the total mass energy content of the universe.
A quarter of everything. And it's dark because it doesn't interact with light.
That's the idea. It doesn't seem to emit, absorb, or reflect light, which is why we can't see it directly. We only infer its presence from its gravitational effects.
Are we trying to detect it directly?
Oh, yes. There are many experiments underway, like the cryogenic dark matter search, trying to catch a dark matter particle interacting, however weakly, with ordinary matter. We're actually more certain about what dark matter isn't than what it is.
Like,
Well, we know it's probably not just dark clouds of normal matter, like dust or non-growing gas. It's not antimatter, because we'd see the annihilation gamma rays. It's probably not made of primordial black holes either.
yeah.
The leading idea is that it's some new type of subatomic particle that barely interacts with anything except through gravity.
Okay, so that's dark matter, about 25%. What's the other big mystery? The 70%.
That would be dark energy. And this one is perhaps even stranger.
Stranger than invisible matter.
Well, for decades, everyone assumed that the mutual gravitational pull of all the matter in the universe should be slowing down the expansion that started with the Big Bang. Like throwing a ball up in the air, gravity should slow it down.
Makes sense. But
In 1998, two independent teams of astronomers were trying to measure this expected deceleration by observing distant supernovae. And they found the exact opposite.
the expansion wasn't slowing down?
It wasn't slowing down. It was speeding up. The expansion of the universe is accelerating.
Wow, okay. How? What's pushing it?
That's the mystery. Whatever is causing this acceleration, we call it dark energy. It seems to act like a sort of anti-gravity, pushing space-time itself apart at an ever-increasing rate.
And this is where Einstein's blunder makes a comeback.
Kind of, yeah. That cosmological constant he introduced to keep the universe static? Well, it turns out something like a cosmological constant, but acting as a repulsive force rather than a balancing one, could explain this acceleration. It seems to be an inherent energy density of empty space itself.
And this makes up the bulk of the universe.
Current estimates put dark energy at around 70% of the universe's total mass energy content.
So let me get this straight. Normal matter stars, planets, gas, us, that's only about 5%. Dark matter is 25%. And dark energy is 70%.
That's the current picture, yes. It's pretty humbling. Everything we're familiar with, everything studied in chemistry and biology is just a tiny sliver of reality.
Are there other ideas about what dark energy could be?
There are a few possibilities being explored. Maybe it's not a constant property of space, but some kind of dynamic energy field, sometimes called quintessence. Or perhaps Einstein's theory of gravity itself needs modification on cosmic scales.
Like MOND, modified Newtonian dynamics.
MOND is one alternative, yes, primarily aimed at explaining galactic rotation without dark matter. There are also ideas like varying speeds of light. But these are generally considered more peripheral theories within the mainstream scientific community right now. The cosmological constant, or something very like it, fits the data best so far.
Okay, one last thing on cosmology before we move on. The Big Bang explains how the universe evolved after it started, but not the actual start, right? The origin question.
That's a crucial distinction, yes. The Big Bang Theory describes the universe from a tiny fraction of a second after the beginning onwards. It doesn't, and can't, tell us what caused the beginning itself, or what, if anything, came before.
But does inflation theory offer any hints? You mentioned something startling earlier.
It does offer a fascinating, though speculative, possibility. Inflation theory suggests that even in the absence of any matter or energy, space-time itself has an inherent tendency to expand exponentially.
Empty space expands.
Yes. And if you consider true nothingness, not just empty space, but no space, no time, no matter, no energy, quantum physics suggests that such a state would be inherently unstable. Quantum fluctuations could spontaneously arise, creating tiny amounts of energy and inflating space-time.
So the universe could potentially pop into existence from nothing, because nothing is unstable.
It's a mind-bending idea, but it offers a scientifically plausible, though unproven scenario for how the universe might have originated from a fundamental quantum instability, rather than requiring some pre-existing perfect state or external cause. It arises naturally from the physics as we understand it.
Okay, that's a lot to chew on. Let's maybe ground ourselves again in the physics happening within the universe. Let's talk astrophysics.
Right, astrophysics.
Yeah.
You described it as applying physics and chemistry to understand stars, galaxies, nebulae, black holes, basically the stuff in space. Exactly. It's the engine that drives much of our understanding. We talked about how the lines blur between astronomy, astrophysics, and cosmology.
Remind us of the distinctions again.
Okay, roughly speaking, astronomy measures what's their positions, brightness, motions. Astrophysics developed the physical theories to explain how these objects work, focusing on small to medium-sized structures. And cosmology takes those physical principles and applies them to the largest structures and the universe as a whole, its origin, evolution, and fate.
So astrophysics provides the tools and understanding that cosmology uses for the big picture story.
That's a good way to put it. In practice, they're deeply intertwined. If you ask, what's this nebula made of? Or how does nuclear fusion work in that star? That's astrophysics. If you ask, how does this nebula fit into the story of galaxy formation and the universe's evolution? That's leaning more towards cosmology, but using astrophysical data. They form this integrated family. Hashtag TAG 3.2 astrophysical tools and aims.
And the history of astrophysics is really tied to applying physics to the heavens, right? Before Newton, it was more descriptive geometry.
Very much so. Newton was the game changer, showing that the same laws of physics apply on Earth and in space. That unification was key.
And that predictive power was amazing, finding Neptune just from wobbles in Uranus's orbit.
Exactly. That ability to predict something unseen based on physical laws is the hallmark of a mature science. That was pure astrophysics in action.
So what are the big goals of astrophysics today? If you ask, say, NASA.
Broadly, they usually frame it around three core aims. First, figure out precisely how the universe works, the physical laws governing it. Second, discover how it began and how it's evolved since the Big Bang. And third, the really exciting one for many people, search for life on planets around other stars.
And since we can't exactly go visit these distant objects, we rely on the light and other radiation they send us, right?
Almost entirely. That's why so much of astrophysics boils down to understanding the mechanisms that produce radiation light, radio waves, X-rays, gamma rays, and how that radiation travels through space and interacts with matter.
Which brings us to spectroscopy. Breaking down light into its component colors or wavelengths?
Absolutely fundamental. Spectral analysis is crucial for all three space sciences. Early spectroscopy was revolutionary. It showed that stars are made of the same elements we find right here on Earth. Helium was even discovered in the sun spectrum before it was found on Earth.
Wow. And it helps sort out those fuzzy patches, the nebulae.
Yes. Spectroscopy revealed that some nebulae were just clouds of glowing gas, while others had the continuous spectrum characteristic of stars. That was a key step in realizing that many of those fuzzy patches were actually entire other galaxies, incredibly far away.
And we owe a major discovery about star composition to Cecilia Payne in the 1920s.
Indeed. Cecile Payne-Gaposchkin, through her spectral analysis, showed convincingly that stars are overwhelmingly made of hydrogen and helium. That overturned the previous assumption that they had a composition similar to Earth.
And the Doppler shift you mentioned earlier, that's also found using spectroscopy.
Yes, by looking at how spectral lines are shifted towards the red or blue end of the spectrum. Astrophysicists can measure how fast stars or galaxies are moving towards or away from us. That, combined with general relativity, was the key evidence Edwin Hubble used to demonstrate the universe's expansion.
We also talked about how Einstein's EMC22 solved the mystery of how stars shine for so long.
Right. Earlier ideas, like stars shining just by gravitational collapse, couldn't explain the billions of years the sun has clearly been burning. EMC22 showed that converting even tiny amounts of mass into energy through nuclear fusion could power stars for vast timescales. It explained their formation, life, and death.
And this loops back to the stardust idea and the specific scientists who figured out element creation.
Yes, that landmark 1957 paper by Margaret and Jeffrey Burbidge, William Fowler, and Fred Hoyle, often called the BFH paper, they meticulously worked out the nuclear processes by which stars fuse lighter elements into heavier ones as they age.
Creating things like carbon, oxygen, iron.
Exactly. And then when massive stars explode as supernovae, they scatter these elements across the galaxy, enriching the interstellar medium from which new stars and planets form.
So the iron in our blood, the calcium in our bones.
Forged in the hearts of long-dead stars. Astrophysics tells us, quite literally, we are stardust.
Okay, let's zoom out again. To the truly massive structures, galaxies. These huge collections of dust, gas, billions of stars, their solar systems, all held together by gravity.
Island universes, as they were once called.
Huh.
We live in one, the Milky Way, which we now know has a supermassive black hole lurking at its center.
And the number of them is just staggering.
Completely staggering. You mentioned the Hubble observation finding 10,000 galaxies in a tiny speck of sky. Current estimates suggest maybe 100 billion galaxies, perhaps even more, in the observable universe alone.
And sometimes they bump into each other.
They do. Galaxy collisions and mergers are a key part of how galaxies evolve over cosmic time. Our own Milky Way is actually on a collision course with our nearest large neighbor, the Andromeda Galaxy.
When's that due? Should we worry?
Don't cancel your plans just yet. It's expected in about 5 billion years. And even when galaxies collide, it's mostly empty space. While the overall structure emerges and gravity rearranges things dramatically, the chances of individual stars or planets actually hitting each other are incredibly tiny because the distances between them are so vast. It's more like two swarms of bees flying through each other.
Okay, good to know. So what are the basic components holding a galaxy together?
It's primarily gravity acting on stars, gas, dust, and crucially, that large component of dark matter we discussed.
Dark matter again, providing the scaffolding.
Providing a lot of the gravitational glue, yes. Most large galaxies also seem to have supermassive black holes at their cores. These are thought to be engines powering the most energetic phenomena we see, like active galactic nuclei, AGN, and quasars.
Quasars are the really bright ones.
The most luminous objects in the universe, yes, believed to be powered by matter falling into those central supermassive black holes.
How do astronomers categorize galaxies? They don't all look the same.
No, they don't. The most common system is based on one developed by Edwin Hubble, later refined by Gerard de Vaucouleurs. It classifies galaxies based on their visual appearance, their morphology. There are three main types.
Okay, what's the most common?
That would be spiral galaxies, like our Milky Way and Andromeda. They're characterized by these large, rotating disks of stars, gas, and dust, often with prominent spiral arms.
And a bulge in the middle.
Yes, usually a central bulge of older stars. Many spirals also have a distinct bar-shaped structure of stars running through the center. We call those barred spirals. The Milky Way is likely a barred spiral. They're embedded in large halos of dark matter.
Okay, spirals. What's next?
Elliptical galaxies. These look more like smooth, featureless ovals or spheres, sort of egg-shaped. They tend to be found in the denser environments of galaxy clusters.
Are they different inside too?
Yes, significantly. Ellipticals are mainly composed of older, redder stars. They generally lack the cold gas and dust needed to form new stars, so there's very little active star formation happening in them. They come in a huge range of sizes, from small dwarfs to giant ellipticals dominating clusters.
And they also have central black holes.
It's now thought that pretty much all massive elliptical galaxies host a supermassive black hole, and the mass of the black hole seems to be closely related to the properties of the galaxy bulge itself.
Interesting connection. Okay, spirals, ellipticals. What's the third type?
Irregular galaxies. As the name suggests, these lack the clear, well-defined structure of spirals or ellipticals. They often look chaotic or disrupted.
Any examples we can see?
The Magellanic Clouds, two small satellite galaxies orbiting the Milky Way, are classic examples of irregulars. They often result from gravitational interactions or collisions with other galaxies that mess up their shape. Smaller ones, called dwarf irregulars, are thought to resemble the very first galaxies that formed in the early universe.
All right, let's bring the focus right back home to our own cosmic neighborhood, the solar system. The sun and everything gravitationally bound to it.
Our local patch of the universe.
Yeah.
And the structure is really dominated by the sun. It contains something like 99.8% of the total mass of the entire system.
Wow. And most of the rest is?
Jupiter. It accounts for more mass than all the other planets combined.
So the planets, we usually split them into two groups, right? Inner and outer.
That's right. The four inner planets, Mercury, Venus, Earth, and Mars, are the terrestrial planets. They're relatively small, dense, and rocky, made mainly of metals and silicate rocks.
They're kind of planets.
Our home turf, yeah. Then beyond the asteroid belt, you have the four outer planets, the giant planets. These are much larger and less dense.
Gas giants and ice giants.
Exactly. Jupiter and Saturn are the gas giants, primarily composed of hydrogen and helium, like mini-stars that didn't quite ignite. Uranus and Neptune are the ice giants. They have substantial rocky cores, but their bulk is made of ices like water, methane, and ammonia under extreme pressures.
And beyond the planets, it doesn't just stop at Neptune.
Not at all. Between Mars and Jupiter lies the asteroid belt, populated by millions of rocky bodies, remnants from the early solar system.
Leftover building blocks.
Pretty much. Then beyond Neptune, you enter the realm of the trans-Neptunian objects. First is the Kuiper Belt, a disk-shaped region containing icy bodies, including dwarf planets like Pluto, Eris, Makemake, and Haumea.
Source of many comets.
The source of short-period comets, yes. Beyond the Kuiper Belt is the scattered disk, a more sparsely populated region of icy bodies with more eccentric orbits. And much, much further out, thousands of times further than Pluto, is the hypothetical Oort cloud.
Hypothetical.
Well, we haven't observed it directly, but it's thought to be a vast spherical shell of trillions of icy bodies, the reservoir for long-period comets that occasionally swing into the inner solar system.
And the whole system is moving through the galaxy.
Right. We're located in the Orion Arm, one of the Milky Way spiral arms, about 26,000 light-years from the galactic center. The solar wind from the sun carves out a bubble in the interstellar medium called the heliosphere, which extends out roughly to the edge of the scattered disk. Hashtag tag 4.2 planetary deep dive. Specific details.
Okay, let's do a quick flyby of the planets themselves, hitting some memorable facts. Starting closest to the sun, Mercury.
Tiny, cratered, and extreme. Daytime temperatures hit 840 degrees Fahrenheit, hot enough to melt lead. But with virtually no atmosphere to trap heat, the night side plummets to hundreds below freezing. A day on Mercury is long, too, about 59 Earth days.
Next out, Venus, often called Earth's twin, but not really hospitable.
Not at all. It's actually hotter than Mercury on the surface, thanks to a runaway greenhouse effect from its incredibly thick, toxic carbon dioxide atmosphere, constant sulfuric acid clouds. And it rotates incredibly slowly, backwards compared to most other planets. A day on Venus is longer than its year.
Bizarre. The Greeks thought it was two different objects.
Yeah, because it appears either as the morning star just before sunrise or the evening star just after sunset. Took a while to realize it was the same planet. Its orbit is about 225 Earth days, but its day is 241 Earth days long.
Then Earth, our oasis, water world. Anything particularly striking from an astronomical perspective?
Well, the fact that it is a water world is pretty special. Also, its relatively large moon, its active geology, its magnetic field protecting us, and it's spinning pretty fast, about 1,000 miles per hour at the equator, while orbiting the sun at a brisk 18 miles per second.
Okay, moving outwards. Mars, the red planet.
Icy, dusty cold. Gets its reddish color from iron oxide rust, basically. It has the largest volcano in the solar system, Olympus Mons, and a huge canyon system, Valles Marineris. Lots of evidence suggests ancient Mars was warmer and wetter, possibly with lakes or even oceans. Could it have supported life? That's the big question driving exploration.
But its atmosphere is too thin now for liquid water.
Too thin for liquid water to last long on the surface, yes. It mostly boils away or freezes. A Martian year is about 687 Earth days.
Now for the giants. Jupiter, king of the planets.
Absolutely massive, more than twice the mass of all other planets combined. Mostly hydrogen and helium gas. Famous for its Great Red Spot, a gigantic storm, larger than Earth, that's been raging for centuries. It has an incredibly strong magnetic field and dozens of moons. Io, Europa, Ganymede, Callisto are the big four. It really is like a miniature solar system. And it spins incredibly fast. A day is less than 10 Earth hours.
Wow. Next, Saturn, the one with the rings.
Iconic. Those stunning rings are made mostly of ice particles, ranging from tiny grains to chunks as big as houses. Galileo first saw them, but his telescope wasn't good enough to resolve them properly. He thought Saturn had ears or handles instead of a gas giant, mostly hydrogen and helium, slightly smaller than Jupiter. A day is about 10.5 Earth hours.
Then Uranus, the tilted one.
The oddball, yes. Seventh planet. Its axis of rotation is tilted almost 98 degrees relative to its orbital plane, so it essentially orbits the sun lying on its side.
What does that do to its seasons?
Makes them incredibly extreme. Each pole gets about 42 years of continuous sunlight, followed by 42 years of darkness. It's an ice giant with methane in its atmosphere, giving it a pale blue-green color. Its orbit takes about 84 Earth years.
And finally, Neptune, the distant blue world.
Eighth and most distant planet. Another ice giant similar in size to Uranus, but a deeper blue color, also due to methane. Known for having the fastest winds in the solar system, reaching supersonic speeds.
And it was found using math.
Yes. Astronomers noticed Uranus wasn't quite following its predicted path, suggesting the gravity of an unknown planet further out was tugging on it. Alexis Bouvard predicted its existence, and Johann Galle found it in 1846, very close to the predicted position. A triumph for celestial mechanics. Its orbit takes about 165 Earth years.
I can't forget Pluto. Still a planet in our hearts, maybe.
Well, officially reclassified as a dwarf planet in 2006 by the International Astronomical Union. It's much smaller than the main planets, smaller even than Earth's moon. It's in the Kuiper belt, has a very eccentric and inclined orbit, tilted by 17 degrees.
And sometimes it's closer than Neptune.
That's right. Because of its eccentric orbit, Pluto was actually the eighth planet from the Sun between 1979 and 1999. NASA's New Horizons mission gave us our first close-up look in 2015, revealing a surprisingly complex and varied icy world. Hashtag tag 4.3 minor solar system bodies. Beyond the planets and dwarf planets, we have the smaller stuff. Comets, for instance.
Dirty snowballs.
That's the classic description. They're relatively small bodies, maybe a few kilometers across, made mostly of volatile ices, water ice, frozen carbon dioxide, ammonia, methane mixed with dust and rock.
And they develop tails near the sun.
Yes. As the comet gets closer to the sun, the heat vaporizes the ices, releasing gas and dust. This forms a fuzzy cloud around the nucleus called the coma, and the solar wind and radiation pressure push this material away, creating the characteristic long tails, often one dust tail and one ion gas tail.
Where do they come from?
Short-period comets, those with orbits under 200 years, mostly originate from the Kuiper belt. Long-period comets with orbits of thousands or even millions of years are thought to come from the much more distant Oort cloud.
Okay. And asteroids. They're different.
Yes, asteroids are primarily rocky or metallic bodies, sometimes called minor planets or planetoids. They range in size from pebbles up to Ceres, the largest asteroid, also classified as a dwarf planet, which is nearly 1,000 kilometers across.
But most are much smaller.
Oh, yes. Their total combined mass is actually less than that of Earth's moon. Most of them reside in the main asteroid belt between Mars and Jupiter.
Are there asteroids elsewhere?
Yes. There are groups like the Trojans, which shared Jupiter's orbit, and then there are the near-Earth asteroids, NEAs, groups called Amors, Apollos, and A10s, whose orbits bring them close to Earth and sometimes cross Earth's path. These are the ones we monitor for potential impact hazards.
All right, let's pivot from rocks and snowballs to the truly extreme, black holes. Not empty space, right? But the opposite.
Exactly the opposite. A black hole is an enormous amount of matter crushed into an incredibly small volume. The example given was a star 10 times the sun's mass squeezed into the size of New York City. The density is just staggering.
And the gravity is so strong.
So strong that nothing, not even light itself, can escape once it crosses a certain boundary, called the event horizon.
And Einstein predicted these.
His theory of general relativity predicted their existence, yes. If the leftover core of a massive star after it explodes is more than about 3 times the mass of our sun, gravity will inevitably overwhelm all other forces and crush it down into a singularity, forming a black hole.
So if light can't escape, how on earth do we find them? We can't see them.
We can't see the black hole itself, but we can see its effects on its surroundings.
Like what?
If a black hole is near another star, it can pull gas off that star. As this gas spirals inwards toward the black hole, a process called accretion, it gets incredibly hot and compressed, emitting intense X-rays and sometimes gamma rays just before it disappears across the event horizon. We can detect that radiation.
So we see this scream of matter falling in.
That's a dramatic way to put it, but yes. Black holes can also distort the light from stars behind them through gravitational lensing, or we can track the orbits of stars moving very quickly around an unseen massive object, inferring a black hole must be there. They can also power enormous jets of particles and tear apart stars that get too close.
How does a star actually become a stellar black hole?
It starts with a very massive star, much bigger than our sun. When that star runs out of fuel, its core collapses under its own gravity. If the core's mass is above that critical limit, around 3 solar masses, the collapse doesn't stop in forming a neutron star. It continues all the way down to a singularity.
And the event horizon forms around it.
Right. As the collapsing material approaches this boundary, something weird happens according to general relativity. Time slows down relative to a distant observer.
Right.
From our perspective, the surface of the star would seem to freeze just as it reaches the event horizon, becoming dimmer and redder. It becomes this frozen star image, though the material itself has actually fallen through.
And they come in different sizes. You mentioned stellar ones.
Yes, there were broadly 3 types based on mass. Primordial black holes are hypothetical, possibly formed in the very early universe, and could range from the mass of an atom up to a mountain. Stellar black holes are the common ones, formed from collapsing massive stars, typically a few times to maybe 20 times the sun's mass. We think there are millions scattered throughout the Milky Way.
And the really big ones.
Supermassive black holes. These reside in the centers of most large galaxies, including our own Milky Way. They are truly enormous, millions to billions of times the mass of the sun. The one at the center of our galaxy, Sagittarius A, is about 4 million solar masses. We see evidence of incredibly hot gas swirling around it.
Let's talk about that weird time stuff again. Time dilation near a black hole.
It's a direct consequence of general relativity. Gravity warps space-time. The stronger the gravity, the more space-time is warped, and the slower time passes relative to a region with weaker gravity.
So if I watch someone fall into a black hole,
From your safe distance, their clock would appear to tick slower and slower as they approach the event horizon. Their image would get redder and dimmer, eventually fading out as they seem to freeze at the edge.
but from their perspective,
From their perspective, ignoring the lethal tidal forces, time would pass normally as they crossed the event horizon. They wouldn't necessarily notice anything special at that exact moment, though they would be irrevocably trapped.
okay, so they're dangerous if you get too close. What about wormholes? Are they related?
Wormholes are theoretical tunnels through space-time that could potentially connect distant points in the universe, or maybe even different universes. General relativity allows for solutions that look like wormholes, but we have no evidence they actually exist. In current physics, lacking a unified theory of quantum gravity, can't really say for sure if they're possible or stable.
So don't count on them for interstellar travel just yet. And we should mention that nearby black hole candidate, V4641 Sagittarius.
Yes, there was some historical confusion there. It was initially thought to be relatively close, maybe 1,600 light-years away, which caused a bit of a stir, but later measurements placed it much further out, more than 20,000 light-years away. So no immediate danger there.
All right, moving from ultimate destruction to places of creation. Nebulae, Latin for cloud, right? These huge clouds of gas and dust.
Exactly. Giant clouds primarily made of hydrogen and helium gas, plasma, and interstellar dust. They are often the birthplaces of stars' cosmic nurseries.
How do they form? Just from the stuff between stars?
Pretty much. The space between stars isn't perfectly empty. It's filled with the interstellar medium, or ISM. It's incredibly tenuous, mostly gas, about 75% hydrogen, 25% helium, plus about 1% dust grains. On average, maybe 1 atom per cubic centimeter,
Compared to Earth's atmosphere.
which has about 30 quintillion molecules per cubic centimeter. So the ISM is an extremely good vacuum by Earth standards, but space is vast.
So over huge distances, that thin stuff adds up.
Exactly. A nebula forms when some region of the ISM becomes dense enough, often triggered by things like shock waves from supernovae or galactic collisions, that its own gravity causes it to start collapsing.
And stars form in the collapsing cloud.
Right. Clumps within the nebula contract, heat up, and eventually ignite nuclear fusion in their cores, becoming stars. Nebulae can be enormous, hundreds of light years across. But even though they're denser than the surrounding space, they're still incredibly diffuse. A nebula the size of Earth would only weigh a few kilograms.
What are the different kinds of nebulae we see?
Astronomers classify them into a few main types based on how they look and how they emit or reflect light. The broadest category is diffuse nebulae, which don't have sharp boundaries.
And within that,
You have emission nebulae, often called HII regions. These glow brightly because the gas inside, mostly hydrogen, is ionized, stripped of its electrons by the intense ultraviolet radiation from hot young stars embedded within them. They emit light at specific wavelengths, giving them distinct colors, often reddish from hydrogen alpha emission. The Orion Nebula is a famous example.
Okay, emission nebulae glow on their own. What else?
Then there are reflection nebulae. These don't produce their own visible light, but instead shine because they're reflecting the light from nearby stars. Since dust grains scatter blue light more efficiently than red light, reflection nebulae often appear blue. The Pleiades star cluster is surrounded by beautiful blue reflection nebulae.
So glowing red ones and reflecting blue ones, what if a cloud doesn't have a nearby star?
Then you get dark nebulae. These are dense clouds of gas and dust that are opaque, blocking the light from stars or bright nebulae behind them. They appear as dark patches or silhouettes against the background sky, like the famous Horsehead Nebula. They still emit radiation, though, particularly microwaves and infrared from the cold dust.
Are there nebulae associated with stars dying, not being born?
Yes, definitely. We have supernova remnants. These are the expanding shells of gas and debris thrown off when a massive star explodes. The Crab Nebula is a prime example, the remnant of a supernova seen in 1054 CE. They often contain exotic objects like neutron stars or pulsars at their center.
And one more type, planetary nebulae. Are they related to planets?
Confusing name, isn't it? No, they have nothing to do with planets. Planetary nebulae are formed when a lower mass star, like our Sun, reaches the end of its life. It swells up into a red giant and gently sheds its outer layers of gas into space. The hot, dense core left behind a white dwarf emits intense UV radiation that ionizes this ejected gas, causing it to glow. They often have beautiful, complex shapes.
And there's a short phase before that.
Yes, the protoplanetary nebula phase. It's a very brief transitional stage as the star is shedding its layers, but before the central star is hot enough to fully ionize the surrounding gas.
People have been noticing these fuzzy patches for a long time.
Oh, yes. Ptolemy mentioned some nebula stars back around 150 CE. The Crab Nebula supernova was recorded by Chinese and Arab astronomers in 1054. With telescopes in the 17th century, observers like Huygens started seeing more detail, like in the Orion Nebula.
And catalogs started appearing.
Right. Halley made a list, then Charles Messier compiled his famous catalog in 1781 to help comet hunters avoid confusing these fuzzy objects with actual comets. His list includes nebulae, star clusters, and even galaxies.
When did they figure out some were gas and some were stars?
A key step was in the 1860s when William Huygens used spectroscopy. He found some nebulae had emission line spectra, characteristic of glowing gas, while others had continuous spectra like stars. That helped distinguish true nebulae from distant galaxies. And as you mentioned, Edwin Hubble in 1922 really clarified that most nebulae are associated with stars and illuminated by starlight.
Okay, let's talk about those stellar explosions themselves. Supernovae,
Yep.
the incredibly violent end for some stars.
The most powerful explosions in the universe, yes. A single supernova can briefly outshine its entire host galaxy, releasing an unimaginable amount of energy. The source mentioned 10 times the sun's power output per second. Just staggering.
And good news for us, our sun isn't massive enough to go supernova, right?
Correct. Our sun will end its life much more quietly, eventually becoming a white dwarf and forming a planetary nebula. Supernovae are reserved for more massive stars or for white dwarfs in specific situations.
Have we seen them in our own galaxy?
Historically, yes. Tycho Brahe observed one in 1572. Johannes Kepler saw another in 1604. The Crab Nebula comes from one seen in 1054. But strangely, since Kepler's supernova over 400 years ago, none have been definitively observed within the Milky Way, though we see remnants of others and plenty in distant galaxies.
How are they classified? It's not just one type of explosion.
No, there are different mechanisms. The initial classification, by Rudolf Minkowski in 1941, was based on their spectra. Type II supernovae show strong evidence of hydrogen lines in their light. Type I supernovae lack hydrogen lines.
Seems simple enough initially.
It did, but later observations, especially after a famous supernova in 1987, showed type I needed further subdivision. So now, Type PS supernovae are type I explosions that do show a strong spectral feature of silicon. Type B of supernovae lack silicon, but sometimes show helium. And type I lack both silicon and helium. EB and IC are often grouped together as type EBC.
Does where they happen tell us anything about what causes them?
Absolutely. Type II and type IB supernovae are found almost exclusively in the arms of spiral galaxies and in irregular galaxies, places where massive stars are actively forming. They're rarely, if ever, seen in elliptical galaxies, which mostly contain old stars. This strongly suggests they come from the deaths of young, massive stars.
And type E?
Type E supernovae, on the other hand, are seen in all types of galaxies, spirals, ellipticals, irregulars. And they often occur far away from active star-forming regions. This points towards them originating from older, lower-mass stars.
Okay, so let's get into the proposed mechanisms. How does a massive star explode? Type 2 IBC.
It starts with stars significantly more massive than the Sun, say over 8 solar masses.
Yeah.
Throughout their lives, they fuse progressively heavier elements in their cores. Hydrogen to helium, helium to carbon, then oxygen, neon, silicon.
Until they hit iron.
Exactly. Iron is the end of the line for fusion energy generation. Fusing iron nuclei actually consumes energy rather than releasing it. So once the star's core becomes pure iron, it can no longer produce the outward pressure needed to counteract gravity.
And
Catastrophic collapse. The iron core implodes in a fraction of a second. The immense pressure crushes protons and electrons together to form neutrons, releasing a flood of neutrinos. The core collapse halts when it becomes an incredibly dense ball of neutrons, a neutron star.
and the explosion.
The infalling outer layers of the star crash onto this newly formed, rigid neutron star and rebound violently outwards. This rebound, possibly boosted by the neutrinos, creates a powerful shock wave that blasts through the rest of underlying star, tearing it apart in the supernova explosion. These are the Type 2 IB and IAC events.
What if the star is really massive?
If the initial star is extremely massive, the core collapse might be so overwhelming that even the neutron pressure can't stop it. In that case, the core collapses completely to form a black hole instead of neutron star.
Okay, that covers the massive stars. How do you get a Type Ia explosion from a lower mass star?
This involves a white dwarf. A white dwarf is the remnant core left behind after a star like our Sun exhausts its nuclear fuel. It's incredibly dense, supported against gravity by electron degeneracy pressure.
But there's a limit to that pressure.
Yes, the famous Chandrasekhar limit, calculated by Subramanian Chandrasekhar. A white dwarf cannot be more massive than about 1.4 times the mass of our Sun.
So what happens if it gains more mass?
The leading theory for Type Ia supernovae involves a white dwarf in a binary star system. If the white dwarf pulls enough material, mostly hydrogen or helium, off its companion star, its mass can creep up towards the Chandrasekhar limit.
And when it hits the limit?
As it approaches 1.4 solar masses, the conditions in the core become hot and dense enough to ignite runaway carbon fusion. Because the white dwarf is supported by degeneracy pressure, which doesn't depend on temperature like normal gas pressure, the fusion spreads explosively throughout the entire star in seconds.
Boom.
Boom. The white dwarf is completely obliterated in a thermonuclear explosion, a Type Ia supernova. No remnant like a neutron star or black hole is left behind.
And these explosions have profound consequences for the universe, don't they? Beyond just being spectacular.
Immense consequences. Firstly, they are crucial for creating and distributing heavy elements. While stars create elements up to iron, supernovae are thought to be the primary sites where elements heavier than iron are synthesized through rapid neutron capture processes during the explosion itself.
So gold, silver, uranium,
You
made
know,
in supernova.
That's the leading theory, yes. And then the explosion scatters all these elements, both those made during the star's life and those made in the explosion, out into the interstellar medium.
Enriching the gas for future generations of stars and planets.
Exactly. Our Sun is a later generation star, relatively rich in these heavy elements, metals to astronomers, compared to the very first stars. We wouldn't have rocky planets like Earth or the elements needed for life without previous generations of stars living and dying, many in supernovae. The source even boldly states, supernovae are supposed to be directly responsible for us everything.
A powerful claim. Any other consequences?
Yes, supernovae are also major sources of cosmic rays, extremely high-energy particles, mostly protons and atomic nuclei, zipping through space at near light speed. These cosmic rays constantly bombard Earth, and it's been suggested they might play a role in biological evolution by causing genetic mutations.
Okay, for our final section, let's come right back to our celestial doorstep and look at the most familiar object in the night sky, the moon, Earth's only natural satellite.
Our constant companion. And it has some fascinating features. For instance, it always shows us the same face.
Tidal locking, right?
Exactly. It takes the moon the same amount of time, about 27.3 days, to rotate once on its axis as it does to complete one orbit around Earth. So one side always faces us.
And it's surprisingly large compared to Earth, isn't it, for a moon?
It is. Its diameter is over 2,100 miles, which is actually larger than the dwarf planet Pluto. While its mass is much smaller than Earth's, its size relative to its parent planet is unusually large compared to most other moons in the solar system. And that large relative size has significant consequences for Earth.
Before we get to those, how did we get such a big moon? What's the formation theory?
The leading theory, the one that best fits the evidence, is the giant impact hypothesis.
It's a big whack.
The big whack, yeah. The idea is that fairly early in the solar system's history, maybe around 95 million years after its formation, a Mars-sized protoplanet, sometimes called Theia, collided obliquely with the still molten embryonic Earth.
A catastrophic collision.
Immense. It would have blasted a huge amount of vaporized rock and debris from both bodies into orbit around Earth. This debris eventually coalesced under gravity to form the Moon.
What's the evidence for this?
Several things. The Moon's composition is remarkably similar to Earth's mantle, suggesting it formed from Earth material. It's depleted in volatile elements that would have boiled off in the heat of the impact, and computer simulations show such an impact could indeed form a moon with the right mass and orbital characteristics.
Are there other ideas?
There are alternatives, like the idea that Earth captured a preformed moon, or that the moon formed alongside Earth from the same accretion disk, or maybe even that two smaller moons collided to form our current one. But the giant impact model currently explains the observations best.
What's the moon like inside? Is it just rock?
It has structure. It likely has a very small core, maybe only 1–2% of its mass, probably mostly iron with some sulfur. Above that is a partially molten boundary layer, then a thick mantle of dense rocks rich in magnesium and iron, and finally the crust.
And the surface we see, craters everywhere.
Stony, dusty, and heavily cratered, because there's no atmosphere or weather to erode them away. The dark patches, the maria or seas, are vast plains of ancient volcanic basalt flows. The lighter highland areas are older, more heavily cratered crust. Composition-wise, the surface is dominated by oxygen, about 43%, silicon 20%, magnesium 19%, iron 10%, plus calcium, aluminum, titanium, and traces of other things, including hydrogen, possibly from water ice.
Water on the moon.
Yes, modern orbiters have found evidence of water ice, particularly hidden in permanently shadowed craters near the poles. Also, hundreds of pits or caves that could potentially shelter future explorers from radiation and temperature extremes.
And its orbit isn't perfectly circular.
No, it's elliptical. Its closest point to Earth, perigee, is about 225,700 miles away. Its furthest point, apogee, is about 252,000 miles. The average distance is roughly 238,855 miles. Hashtag 5.2 Earth orbit connection in eclipses.
So this big moon orbiting us, what effects does its constant gravitational pull have down here on Earth?
The most obvious effect is the tides. The moon's gravity pulls more strongly on the side of Earth facing it, creating a bulge in the oceans. But it also pulls less strongly on the opposite side, allowing inertia to create another bulge there.
So high tide happens on both the near side and the far side.
Roughly, yes. As Earth rotates underneath these bulges, coastal areas experience 2 high tides and 2 low tides each day. The sun also contributes to tides, but the moon's effect is stronger because it's so much closer.
And the moon's gravity is actually slowing Earth down.
It is. The friction from these tidal bulges dragging across the Earth acts like a brake on Earth's rotation. It's a very slow process, but it's increasing the length of our day by about 2.3 milliseconds per century.
Tiny, but it adds up over geological time, and the moon is moving away.
Yes, that energy Earth loses in its rotation has to go somewhere. It gets transferred to the moon, boosting it into a slightly higher orbit. The moon is currently receding from Earth at a rate of about 3.8 centimeters or 1.5 inches per year.
Wow, so billions of years ago the moon was much closer and days on Earth were much shorter.
Exactly. And there's another crucial stabilizing effect.
What's that?
The moon's gravity helps stabilize the tilt of Earth's axis. Without the moon's steadying influence, Earth's axial tilt might wobble much more dramatically over time, leading to extreme climate swings that could have made it much harder for complex life to evolve and persist. The moon may have been key to making Earth a livable planet.
Okay, finally, the spectacular alignments. Eclipses.
These happen when the sun, Earth, and moon line up in specific ways. A lunar eclipse occurs when Earth passes directly between the sun and moon. Earth's shadow falls onto the moon, darkening it or turning it reddish. This can only happen during a full moon.
And a solar eclipse.
A solar eclipse happens when the moon passes directly between Earth and the sun. The moon's shadow falls onto a small part of Earth, blocking out the sun's light. This can only happen during a new moon phase. Because the moon and sun appear roughly the same size in our sky, a fantastic coincidence, the moon can sometimes perfectly cover the sun's bright disk, creating a total solar eclipse, one of nature's most awe-inspiring spectacles. Hashtag outro.
And that brings us to the end of this, well, truly cosmic deep dive. We've covered an enormous amount of ground, from the very origins of the universe in the Big Bang and inflation,
Through the fundamental physics governing stars, galaxies, and black holes, astrophysics.
all the way to the biggest remaining mysteries, that huge hidden sector of dark matter and dark energy.
And despite all the incredible progress we've made, from Ptolemy trying to map the planet's paths to Hubble revealing the expanding universe and beyond, we keep coming back to that humbling fact.
That only 5% of the universe is the normal stuff we understand reasonably well.
Exactly. Which really raises the crucial question for the future, doesn't it? What fundamental insights can we gain from studying this visible 5% that will finally help us unlock the secrets of the other 95%? That's the frontier.
And thinking back to the very beginning, the source material left us with that provocative idea about origins.
Right, the idea that if you had a true nothing, no matter, no energy, not even space or time quantum physics, suggests it might be inherently unstable. That instability itself could potentially trigger the spontaneous creation of matter, energy, and expanding spacetime.
So existence itself might arise not from some perfect static beginning, but from fundamental instability, a universe born from asymmetry, not symmetry.
It's a profound thought, definitely something to mull over long after this deep dive. The possibility that the default state isn't perfect balance, but dynamic potential.
Indeed. We hope this journey through the cosmos has given you a new perspective on our place within it, and perhaps sparked even more curiosity about the universe's ongoing story.
There's still so much to discover. Thanks for diving deep with us today.